We're in a position in the world at the moment where energy is, well, it's critical. It's critical to diplomacy, it's critical to politics, it's critical to everything that we do in our everyday lives. And I think we all know that we are in what's called the energy transition. So what we're going to talk about today is some technology which fits into the energy transition, and it also fits into how we can start to understand the subsurface for storing carbon dioxide as part of that energy transition and part of meeting our net zero 2050 goals. So, the Global CCS Institute is very happy to report that we have increased CCS capacity massively from 2020 to 2021. However, they also say that what we need to do to achieve 2050 goals is to increase that capacity by about another 2 to 3 orders of magnitude. So, where's the UK on this adventure? Well, at the moment, we have 4 hubs in the UK which are not in production and not storing CCS. However, just last month, there were 13 new licenses released to be utilised by people by entities for storing carbon dioxide. However, the government organisation that released them says we need to have more than 100 more such storage sites just to meet the UK's 2050 targets. So, as you can imagine, if you want to store gas or fluids, as it will be in the Earth, inside the Earth, you've got to understand what's happening there to allow you to make smart decisions along your pathway. So, subsurface imaging is kind of the way by which we can contribute to doing that. We've been doing it for a long time in terms of hydrocarbon exploration, oil and gas exploitation. And some of the principles are absolutely applicable to carbon dioxide storage. So if we can generate really detailed, high-resolution, accurate images, we can start to figure out where we're going to store our carbon dioxide. And by doing so, we can also, hopefully, in the future, start to monitor that carbon dioxide in the subsurface. Where is it moving to? Is it staying where we modelled it to? Is it staying where we expect it to? Is it leaking? Is it causing any risk within that? And if we can start to do those things successfully, then we can move forward and we can move forward. And what we can actually really look to do is to reduce our own kind of impact and our own cost of doing that. If we can do it faster, we can have less environmental impact directly in the process. And that's really what the demands of subsurface imaging are today as we stand, mostly for carbon dioxide storage, but equally a little bit still in hydrocarbons. So the tools by which we do that are very much data-driven. We have a particular type of data that we call seismic data. If you mention seismicity, if you mention the word seismic, people tend to assume earthquake. It's not quite what we have here. In fact, what we do is, there we go, perfect. We have a seismic source. It's like a small explosion, and we release that near the surface of the Earth. It emits a lot of sound waves, which then propagate down through the Earth. And where we have these layers of rock, they reflect and they come back, and they're recorded digitally by these receivers, again, near the surface. And in a physical property sense, what causes that is density. Changes in density between rock 1 and rock 2 creates a reflecting boundary, and the energy reflects between those interfaces. So once you record that, you get a lot of raw data, and we record these kinds of data over hundreds and thousands of square kilometers. We record petabytes and petabytes of data now. It's absolutely massive, the amount of data that's being recorded all the time. But this raw data, it's a little bit difficult to deal with because It has a lot of different arrivals within it, all of which we can ultimately extract value from, but in this image, it's incredibly difficult, almost impossible, to actually understand the Earth and its subsurface from here. What we want is an image much more like this one. So this is valuable and this is useful. So this is a three-dimensional image of the inside of the Earth. This is the Earth's subsurface. So what you can see, all these kind of what we call events, these are the reflections that we were talking about over here, now shown in a three-dimensional sense through the Earth. You can start to interpret these, track them, you can add your well data to them. All your subsurface data can be put together to build this great understanding of what's going on deep inside the Earth. And that's the information, that's the value that we can provide, as long as we can actually then provide an accurate image and then extract the value from it. Okay, so one tool which Nick has kind of already talked a little bit about that we can use to do this is full waveform inversion. And where it has big benefits over methods we've been using up to date is it's going to reduce kind of the full timeline. It's going to start with the raw data and then it's going to go all the way straight to a final image. Previously we had many good but long processing steps along the way. It would take us many months to get from point A to point B. We're going to do this now in a much simpler set of steps. Well, not simpler, excuse me, a much lesser amount of steps. So this is our starting point, and I promise you, inside the Earth does not look like this. This is a vastly simplified model which we start from, but it is still our best starting point. By simplifying it so much, we don't input any bias to the system. We don't create any prejudice in the process. We're just going to use our raw data and a very simple starting model. In this case, what we have also is a ground truth by which we can measure against. This is a recording taken actually through the Earth while drilling. So that's a measurement of the velocity, and the grey is the kind of the key ground truth which we've got here. So full waveform inversion, what it does in a simple sense, it takes the raw data and it makes a prediction of that using this velocity model, and then it takes the cost function that Nick was referring to previously and tries to minimize that prediction error, and then we repeat this simulation many times until we've actually matched all the kinematics of the arrivals of that raw data that we recorded and arrived at our final Earth model, which can look like this. In this instance, what we can now see is the blue curve is extracted at the same location as our sonic log, so you can see all the detail and all the resolution is achieved by full waveform inversion. And in this instance, it's a slightly older data set. Someone who understands the Earth and understands the data that we're providing for them can tell us that we have gas reservoirs down here in these thin, slow velocity layers. So, in terms of building images of the Earth, FWI is an incredibly powerful but very accurate process. And in many respects, you can really consider it to be a digitalization of Earth imaging. So it is going to give us, and we can show it all the time now, a more accurate result. It can give us higher resolution, just as we've shown in that previous image. But it's more automated, so it's free of human intervention. It doesn't have that kind of inherent bias or particularly any interpretive elements to it. We can run it now faster and faster. We can get to great results a lot faster than we previously could. Mostly that's through the enablement of cloud computing, which also makes us extremely scalable. This example on the right was made in 6 weeks using FWI. The traditional methods would have taken several months to do it. That specific example was done by one of our partners, and they ran that alongside a processing company running it traditionally, and they got a better result in a lot faster amount of time. So, how do we apply that to the carbon dioxide storage world? Well, the first step of any carbon dioxide process is what they call now site screening. So if you have built this wonderful image and in detail and resolution of the subsurface, you need to understand it. So it will tell you about the volume and the size by which you can store gas within it. It will tell you about how well sealed it is and your probabilities that your gas may escape through that seal. It will also tell you how well connected different parts of it are, so you can model how your carbon dioxide will be moving once you start to inject it. And those are really key criteria to deciding where we're going to inject carbon dioxide. And this is an example from the Acorn Hub off the coast of Scotland. So they started with 113 possible locations, and they went all the way down and only selected 6. So you can see really clearly here that this criteria-driven approach requires very, very accurate data to select the sites where you're going to invest tens of millions of dollars and tens of years in storing carbon dioxide. So you want accuracy, you want resolution, but you want to get your data fast because you want to be able to extend the time by which someone has to make those decisions and get the confidence in making those decisions. But probably even more importantly, we can go a step further than that in how we monitor when we put it in the ground. There's not many cases where people are doing this yet. There's one really fantastic example in Norway, in the North Sea. It's at a former oil and gas site called Sleipner, and now they are pumping CO2 into the ground here. And the left-hand image is generated from using the traditional methods, whereas the right-hand image is generated using full waveform inversion. And the accuracy and the detail that you can see is quite startling. I will try to highlight what's going on here for you. IP is the injection point. So that's where the carbon dioxide is going into the subsurface. And the low colors, the greener colors, are lower velocities and therefore lower densities. So as you can imagine, putting a gas into the subsurface will give you a lower density and an associated lower velocity. Here, you can make an interpretation of this, but it's really fuzzy. I couldn't really tell you where my CO2 is traveling here. In this version over here, I can see it really, really clearly. If I'm injecting here, my gas is building up into this reservoir here, and it's building into one layer here, and there's a little connecting point, and then it's building to a second layer up here. None of that information is contained in that left-hand image. So this is a really, I mean, this is a spectacular result, but it's all achieved through full waveform inversion. So they're able to do that faster. They don't give it any subjective input, but they can get that amazing, fantastic result, which helps them to make positive decisions and build the right strategies for for how they're going to store gas in the future and how they're going to monitor it, because those are really expensive elements for the types of companies who are doing it. So FWI is really able to meet all the subsurface requirements that we need for CO2 storage, at least in an earth science sense, and how then we can support the engineering that goes with that. So thank you very much. I will hand back to Yash.